Right, now we are looking at a section on Maclaurin series by repeated implicit differentiation. And for this video, we are specifically looking at example 5. So many questions on Maclaurin series actually involve implicit differentiation and repeated differentiation of a differential equation. We look at the first part of this example. So given that y is equivalent to tangent pi over 4 plus x, we are required to show this equation involving y, dy dx, and d2y dx squared. So first thing first, I have to differentiate this equation with respect to x. So on the left hand side, differentiating y with respect to x, I should get dy dx. Right hand side, differentiating tangent pi over 4 plus x, I should get secant squared pi over 4 plus x. So secant squared pi over 4 plus x can be rewritten as 1 plus tangent squared pi over 4 plus x. Why do we particularly write in this manner? Because realize that y is equals to tangent pi over 4 plus x, we can rewrite everything on the right hand side as this. So dy dx is equivalent to 1 plus y squared. Right, earlier we have dy dx equals to 1 plus y squared. Now we differentiate this equation 1 implicitly with respect to x. So on the left hand side, differentiating dy dx, I should get d2y dx squared. Right hand side, differentiating 1, I get a 0. Differentiating y squared, I should get a 2y dy dx. So shown. Okay, the next part of this question is this. By repeated differentiation of this result, find the series expansion of y in ascending powers of x up to and including the term x to the power 4. So by Maclaurin's expansion, we know that fx can be rewritten in this manner, where f0 means the value of y when x is 0, f prime 0 is the value of dy dx when x is 0, f double prime 0 is the value of d2y dx squared when x is 0, f triple prime 0 is the value of d3y dx cubed when x is 0. And in this question, they want us to expand up to and including the term x to the power 4. In other words, I also need to find out what is this value here, whereby this is actually the value of d4y dx to the power 4 when x is 0. Okay, so now we'll move on to differentiate equation 2 implicitly with respect to x. So on the left hand side of equation 2, differentiating d2y dx squared, I should arrive at d3y dx cubed. On the right hand side of equation 2, I can see as a product of 2y and dy dx. 2y and dy dx. So on the right hand side, if I were to differentiate with respect to x, keeping the front 2y, differentiating the back, I will have d square y dx squared, adding the term which includes dy dx keeping the back, multiplied by the differential of 2y, which is 2 dy dx. So eventually we'll get 2 dy dx squared. So of course now we need to find the 4y dx to the power 4. We need to differentiate equation 3 with respect to x again. So on the left hand side of equation 3, differentiating the 3y dx cubed, I will have the 4y dx to the power 4. So on the right hand side, actually I have two terms. The first term is 2y d2y dx squared. So it's actually a product of 2y and the 2y dx squared. So again, let's take product rule. So 2y, I keep differentiating the 2y dx squared, I get the 3y dx cubed plus the back the 2y dx squared multiplying the differential of 2y, which is 2 dy dx. So this is how we arrive here. So the second term, here we can apply chain rule here. So the power 2 will bring it down. We will have 4 dy dx, but we need to differentiate whatever that's inside. So differentiating dy dx, I'll get the 2y dx squared. And we get 4 dy dx, the 2y dx squared. So collecting all the common terms on the right hand side, this is what we arrive. Right now, we are required to find the values of y, dy dx, the 2y dx squared, the 3y dx cubed, and the 4y dx to the power 4 when x is 0. So first of all, let us find the value of y when x is 0. When x is 0, y is equivalent to tangent pi over 4 equals to 1. So substituting y equals to 1 into equation 1, we'll have dy dx equals to 1 plus 1 equals to 2. So this value of 1 is actually the value of y squared. So now I substitute the value of y equals to 1 and dy dx equals to 2 into equation 2. So now we will get the 2y dx squared equals to 2 times 1 times 2. So in this case, the 1 is actually the value of our y. This 2 here refers to the value of dy dx. Right, so now let us substitute the value of y, dy dx, and the 2y dx squared into equation 3. Let's look at equation 3 here. How do I arrive at the value of 16? The value of 1 is the same as what we discussed earlier, which is y. The value of 4 here is actually the 2y dx squared. And the value of 2 here is our dy dx. Right, so the 3y dx cubed is actually 16. Right, finally, we need to find the value of d4y dx4. So d4y dx4, similarly, substituting all the values that we have found earlier, the values of y, dy dx, d2y dx squared, and d3y dx cubed, we are able to get d4y dx4 as 80. So by Maclaurin's expansion, we know that we have to write fx in this manner. And since we have found the value of f0, which is your y, f prime 0, your dy dx, f double prime 0, your d2y dx squared, f triple prime 0, d3y dx cubed, and f4 0, which is d4y dx to the power 4. So substituting all the values inside, you arrive at the final expansion for y.